for convergence and divergence. If you have a geometric series, which looks like this, the sum from n equals, most of these, it doesn't actually really matter where you start. So a lot of them say something like the sum from n equals just a number to infinity of something like a times r to the n. We know this converges if the absolute value of r is less than 1. It diverges if the absolute value of r is greater than or equal to 1. And I'll just point out while we're here, this is very similar to the convergence divergence criteria for the ratio and root test. And then an example of this would be something like the sum, what have I got here? Sure. From n equals 1 to infinity of 2 to the n minus 1 over 3 to the n. This one, it should be relatively clear that our ratio is 2/3, right? You could write this as the sum from n equals 1 to infinity of, oh, how did I do this here? Yeah. 2 to the n over 2 times 3 to the n. And then we can see that our ratio is 2/3. So the absolute value of our ratio is less than 1, so we get convergence. P series, also pretty straightforward. I feel like I didn't give myself enough room on this board, so I'll try and make things fit in, but I have to write some stuff. P series just looks like the sum of 1 over n to the p, and this converges if p is greater than 1, it diverges if p is less than or equal to 1. And that, again, it's good to think about why these things are what they are, right? This is convergent when p is greater than 1 because, right, you have a higher power, so the terms are getting smaller faster. Whereas if p is less than or equal to 1, your power isn't very large, so your terms aren't getting small super fast. And so they're just not small enough that they aren't adding up to infinity, or they are adding up to infinity. And there's lots of examples of this. Yeah, I'm going to use this here. For example, the kind of classic examples I keep in mind is this series diverges, this series converges. Because here, the terms have to go to 0 and they're going to 0 fast. Here, the terms go to 0, but they don't go to 0 fast enough. And there's lots of examples of P series. We could try and make it complicated and write something like, no, we don't make it complicated. Let's just leave it there. Sure. Let's look at the nth term test, which I just erased. So the nth term test, again, also known as the test for divergence, right? This only shows if a series diverges. So right, we need the limit as n goes to infinity of a sub n to be not 0. Then the series diverges. An example of this could be something like the sum from n equals 1 to infinity of, what have I got here? 3n plus 5 over 12n minus 7. So let me ask you guys. I should say, let me ask you girls, you women. I don't know. Let me ask you people. How about that? What's the limit as n goes to infinity of 3n plus 5 over 12n minus 7? Yeah, which is not 0. So this diverges. On the other hand, we know if the limit is 0, that doesn't tell us anything, right? If the limit of the sequence is 0, you have to do more work. So really, really, really want to strongly emphasize the nth term test, also known as the test for divergence, only tests for divergence. It cannot tell you it converges. So then we have direct comparison, which is not in the spot on the list. So, and I will say this handout also has a lot more to say. So like in the handout for direct comparison, it says, it's asked the question, is the series obviously larger or smaller than some known series? For example, 1 over 3 to the n plus 1 is obviously smaller than 1 over 3 to the n. And we know that this converges. So this converges by direct comparison. Or for example, the sum from n equals 2 to infinity of 1 over the square root of n minus 1. Clearly that is bigger than 1 over the square root of n. And 1 over the square root of n is a divergent p-series. So if you're bigger than something that's divergent, you diverge. If you're smaller than something that's convergent, you converge. We could write out the test, but I feel like this kind of says it all. Limit comparison is a little more involved. So limit comparison, basically you're kind of asking yourself the same question. Is it seem like it's similar to something that is convergent or divergent? So is it similar to something convergent or divergent? Most often, in my opinion, used for something that looks like the sum of powers of n over powers of n. This is almost always guaranteed to, for me anyway, to want to use the limit comparison test. I guess I can erase some of this stuff over here. So, for example, if we have the sum from, doesn't really matter, n equals 2 to infinity of, what do we got here, 3n plus 2 over the square root of n times 3n minus 1. This might be bigger than or smaller than something, but I can just compare powers, right? This is looking like n to the first on top. This is looking like the square root of n times n to the first on the bottom. So I'm going to limit compare this with the sum of n over the square root of n times n, or really just 1 over root n, which I know is divergent because it's a divergent p-series. And then we would do the limit as n goes to infinity of the unknown 3n plus 2 over the square root of n times 3n minus 1 divided by the known. Then we, of course, flip and multiply just to make our lives easy. Let's do that here. The square root of n and the square root of n cancel. With the limit as n goes to infinity of 3n plus 2 over 3n minus 1, which is 1. And for the limit comparison test, as long as it's not 0 and not infinity, we're good to go. So check. Since we compared against something divergent, our thing diverges. And then, right, if you're doing the limit as n goes to infinity of an over bn, it's okay to get 0 for convergence, and it's okay to get infinity for divergence. So if I had gotten infinity here, that would have been fine. I could have said my series diverged. If I had gotten 0, though, I would have had to do something else. Okay, so those are some of the tests. Let's look at the other tests. The ratio root test, and we have the integral test. So the ratio test we typically use if we see something to the nth power or n factorial. That's definitely when I'm going to use the ratio test. So we're going to look at the limit as n goes to infinity of the next term over the previous term. And if it's less than 1, sorry, but I tried to fit this all on a couple boards. Obviously, it doesn't all fit. Less than 1, you get convergence. If it's greater than 1, you get divergence. For example, sorry, where did my examples go? Yeah. For example, something like the sum, what have I got here? Sorry, my example of, 3 to the n minus 2 over n factorial from n equals 1 to infinity. So here we would take the limit as n goes to infinity of the n plus 1 term. So it'd be 3 to the n plus 1 minus 2 is n minus 1 over n plus 1 factorial. And then instead of dividing by this, we're going to multiply by the reciprocal. So we're going to get n factorial over 3 to the n minus 2. Okay, So the n factorial over n plus 1 factorial becomes 1 over n plus 1, right? The n fact, this is n plus 1 factorial is n plus 1 times n factorial. This becomes the limit, as n goes to infinity, of 3 to the n minus 1 over 3 to the n minus 2 is 3. And then n factorial over n plus 1 factorial is n plus 1. Limit of this is 0, so which is less than 1. So this converges. For the root test specifically, you get the same sort of condition, right? If the thing you're finding the limit of is less than 1, you get convergence. If it's greater than 1, you get divergence. But here the test is taking the limit as n goes to infinity of the nth root of the absolute value of base of n. Or it might be more convenient to write as the limit as n goes to infinity of the absolute value of n to the 1 over n power. And even though this is a great test, we really only ever want to use it if it's easy to use, right? Basically, if you see something all raised to the nth power or something like times the nth power. For example, the sum from n equals 3 to infinity of what have I got here? Sure. Let's say, I don't know. Sure. N plus 1 over 3n plus 2 to the 2n power. You can totally use the ratio test here. Most of the times when you can use the root test, you can also use the ratio test. But here specifically, since it's everything just to something with multiplied by n, using the root test is really easy. I take the limit as n goes to infinity of all of this to the 1 over n power. Well, that's pretty straightforward. Right, when you have a power to a power, you multiply the powers, and 2n times 1 over n is just 2. That's why we're using it here. So we're going to get the limit as n goes to infinity of n plus 1 over 3n plus 2 to the second power, which is going to be, so n plus 1 over 3n plus 2 goes to 1/3. So we get 1/3 squared, which is 1/9. And since that's less than 1, we get convergence. And then if it's equal to 1, we don't know. And let me see here real quick. Let me grab something. So I'm going to have you guys do a problem for a minute. Sorry, where'd you go? So why don't you try, yeah, sorry, I'm gonna share my screen here. So I would like you guys to try problem 1C here on this page. So we were finding whether or not this series, 3 to the n times n squared over n plus 1 factorial is convergent or divergent. I'm pretty sure we're going to get convergence here. And again, the dead giveaway that we should use the ratio test is that we have a factorial. So we're going to do the limit as n goes to infinity of the n plus 1 term, so 3 to the n plus 1 times n plus 1 squared over n plus 1 plus 1, so n plus 2 factorial, multiply or divided by this and multiplied by the reciprocal of n plus 1 factorial over 3 to the n times n squared. And we group the like things together. Just the limit as n goes to infinity of 3 to the n plus 1 over 3 to the n is just 3. N plus 1 squared over n squared. The limit's going to be 1, but since I haven't taken limit, I'm just going to write n plus 1 squared over n squared. And then n plus 1 factorial over n plus 2 factorial is going to give me an n plus 2 in the denominator. And you can either say, I've got n squared on top, I've got n cubed on the bottom, so the limit's 0. Or you could do the limit factor by factor and say the limit of this part's 0. Sorry, limit of this part's 1. The limit of this part's 0. So you get 3 times 1 times 0, which is 0, which is less than 1, which would mean this converges. Okay. Yeah, the problem's not too bad. couple more examples of the various tests we have, and then I'll get to the question that Mindy asked. And then we'll talk more about power series, and then we'll probably talk about Maclaurin and Taylor series. So the last three tests, I just want to make sure everybody remembers. This one's from a while ago. The integral test. Basically, if you're thinking about using an integral test, you should be asking yourself, okay, so if my series from n equals whatever to infinity of a sub n, the question you should be really asking is well, sorry, so if f of n is equal to a sub n, then the question we should be asking is the integral of f of x easy? Typically, the integral test is kind of one of the things we use last. I think often there is some other test that is just easier to use. An example could be something like the sum from n equal to 2 to infinity of the natural log of n squared over n. Although even for this one, I probably wouldn't use the integral test, but we could. Right? You could do the integral from 2 to infinity of the natural log of x squared over x dx. The integral of this is just like now, like what is it? We could do a u substitution. I don't want to do the u substitution. If u is that, du is that, so it's going to be, I think it's going to be natural log of x cubed over 3. That seems right. I think there's a 3 missing in the answers on this handout. I think there isn't a 3 where there should be a 3. That's okay. So I'm doing this very much the kind of wrong way. Not wrong, but not as precise. But usually we've got the limit as b goes to infinity of the integral from 2 to b, and so on and so on. If we look at this, though, this is still not wrong. And then when you plug in infinity, the natural log of infinity diverges. So this is divergent. Although, to be perfectly frank, we could show this one diverges more easily by using the direct comparison test and saying, oh, natural log of n squared over n is definitely bigger than 1 over n. Or we probably could have even used the limit comparison test with 1 over n to also show divergence. So the integral test really kind of last resort. If nothing else works and it looks like you can integrate it, then we integrate it. Okay, last 2 tests. We have the alternating series test and the test for absolute convergence. There's a couple things to say about both of these. First of all, I would say that if you have an alternating series, if they're just asking about convergence, like they're just asking, does it converge? You should try this first. Because if they just want to know converges, sometimes they usually do this. So yeah, but then let me just say words. You guys like, no, you can't. So for the alternating series test, if we have the sum from n equals 1 to infinity of -1 to the n or n plus 1, doesn't really matter, of a sub n, there are 3 things that have to be true. So this converges if 1, the a sub n's are all positive. So that this is alternating, right? It actually has to be an alternating series to use an alternating series test. 2, the limit of the a sub n's goes to 0. I should point out, if this one fails, we can say it diverges. But if the other 2 fail, it just says nothing. And then 3, the most important one, is it decreasing? So yeah, that's kind of it. An example of this would be the sum from n equals 2 to infinity. What have I got here? Negative 1 to the n times natural log of n over n. We could definitely show that this was, well, 1. In fact, let's do it. Our non-alternating terms are definitely positive. Natural log of n over n is positive. 2, the limit is certainly 0. Limit as n goes to infinity of natural log of n over n. If we use L'Hopital's rule, we get 1 over n over 1, which goes to 0. And then finally, it is decreasing. And the way we usually show decreasing, as long as there isn't a factorial involved, is we just say, okay, well, I'm going to look at the function natural log of x over x, take its derivative and show it's negative. So f prime of x is bottom, derivative of the top, minus top, derivative of the bottom squared. This ends up being 1 minus natural log of x over x squared, which is negative as long as x is bigger than e. So this is certainly decreasing as long as n is bigger than e. So we've met the 3 conditions. It converges by the alternating series test. I would also point out that this series does not converge absolutely. So absolute convergence just says that if the sum of the absolute value of a sub n converges, then a sub n, the sum of a sub n converges as well. If this diverges, we can't say anything about this. We have to do something else. But yeah, I think that's kind of all I want to say. And we often use this, frequently used, if we have, say, like a sine of n or a cosine of n. So we have one of those, and the absolute value lets us be less than or equal to 1. Yeah. So, but I want to say again, because this is a common mistake, if it doesn't converge absolutely, that doesn't mean it diverges. So if something is not absolutely convergent, then we have to check and see if it's alternating series convergent, meaning it would be conditionally convergent, because it wouldn't be absolutely convergent, but it would be convergent. Okay, so those are all the tests. I guess there's one other thing. There's also telescoping series, but I don't think we need to go back to that. It's not really that important. I mean, it's not important, but okay. So those are all the tests. Try to use them when they're most appropriate. I would definitely refer all 2 of you, to that handout, the series handout that is in Canvas, because I think it is useful. And it really does kind of, if you actually read through it, it really does kind of spell out what kinds of things you should be asking yourself when you're trying to use a specific test, or what sorts of things you should see to want to use a certain test. But let's go ahead and look at the question that was asked, which is using a geometric series to represent each of the given functions as a power series about x equals 0. Excellent question. So let's look at this first one. F of x equal to 5 over 3 minus x. Now, from last time, I hope you got, maybe you remember, maybe you don't. We're always looking, if we're trying to write something like this as a power series, as a geometric series, right, specifically, a geometric power series, we're really trying to make this look like 1 over 1 minus r. Because we know that 1 over 1 minus r is 1 plus r squared plus r cubed, so on and so forth. So we are trying to make this look like this format so that we can then express it like this. So if you get 1 over 1 minus r, you can say that that's equal to the sum from n equals 0 to infinity of r to the n. Of course, with the caveat that the absolute value of r has to be less than 1. or our radius of convergence is 1, or our interval of convergence is -1 to 1 for where r is that. Okay, so here, and they also, oh, sorry, and they were even more specific, and the center has to be 0, which it certainly is here. Right? They say the center has to be 0. Yeah, they say about x equals 0. So, yeah, so if you're writing in this format, the center is always 0, right? Because we're saying r has to be less than 1 in absolute value. So we're saying r is between 1 and -1, and the middle of that is 0. So the center being 0 rules out the way I might have done it back when I was a person. So this is not the answer. Although this is technically not incorrect for the first half of it, it is incorrect if we want the center to be 0. You could do something crazy like this. And then write it as, you don't need to write this down if you don't want to, because this is not the right answer. So I could totally write this as 5 times 1 over 1 minus r. 1 over 1 minus r is 1 plus r plus, right? This is 5 times 1 plus x minus 2 plus x minus 2 squared. The problem with this answer, as you might be aware, is that this is centered about 2. And we want our answer to be centered about 0. So instead, we have to do something different. We're trying to get something over 1 minus our r. To get a 1 minus r in the denominator, we have to factor out a 3 from that 3. So I can rewrite 5 over 3 minus x as 5 over 3 times 1 minus x over 3. And then I would personally like to factor out the 5/3. I'm going to write this as 5/3 times 1 over 1 minus x over 3. And our x over 3 is our r. I don't think you need to write out the long thing here, that 1 over 1 minus x over 3 is 1 plus x over 3 plus x over 3 squared plus x over 3 cubed, et cetera, et cetera, et cetera. But I do think you need to be comfortable with saying, okay, this is equal to the sum from n equals 0 to infinity of x over 3 to the nth power. You could leave it like that. Sure, that would be perfectly fine. You could also manipulate it a little bit. If you wanted to bring this 5/3 in, you certainly could. And you could write this as the sum from n equals 0 to infinity. I would probably leave it as 5/3 times x over 3 to the n. But you could also write it as 5 times x to the n over 3 to the n plus 1. I think that's doing you a disservice, though, because you want to have kind of as much as you want to the n so that you can see what your ratio is. So to finish this question, because they do ask a second part, or not a second part, but they ask to find the interval of convergence. So as always with a geometric series, the interval of convergence is always that your ratio is between -1 and 1. In this case, our ratio, the thing that's raised to the nth power, is x over 3. So that if you multiply both sides by 3, we get -3 is less than x is less than 3. So the interval of convergence here is -3 to 3. We don't have to check the endpoints because it's geometric. For other ones where we manipulate it like it's no longer geometric, then you have to check the endpoints. But this one specifically is geometric, right? Every time you're multiplying by x over 3 to get to the next term, and we know that our ratio in a geometric series has to be strictly between -1 and 1. Are there questions about this? It's a good question. Would you like to see how to do part B? I mean, part B is pretty much the same, although it is maybe slightly more complicated. Okay, cool. So, yes. So last time I started talking, so we're going to do more problems like this actually. But specifically, let me grab my notes here. There was something I wanted to make sure I said. Oh yeah, I know what I was saying last time. Yeah. Sure. Okay. So yeah, so when we're talking about power series, we want our ratio to be less than 1. And so for example, so I'm trying to like, yeah, so we're doing a lot of manipulating with things. I feel like we did that one last time, sure. Yeah, and we definitely talked about this one last time. So, sorry, brain, yeah. I feel like I kind of need to give you, so, okay, I know what we'll do. Let's do this. Where'd you go? Sorry, I'm trying to, that's what I want. I think I want that instead. Really? Okay, let's just do this one. Let's say I want to find a series. So find a power series for 1 over 1 plus x squared, 1 minus x squared. So this could be challenging. You might think, and it wouldn't be wrong to think this, but it's not the way we're going to go. You might try thinking, well, this is 1 over 1 minus x times 1 over 1 minus x. And then that one is 1 plus x squared plus x cubed plus and so on. And that's 1 plus x. Right? You could actually try to multiply these infinite series, but it's really kind of, it's not something we never do, but it's something we try to avoid doing. Instead, we're going to use the fact that this is the derivative of something. In fact, the antiderivative of 1 over 1 minus x squared is, I think it's 1 over 1 minus x. I should probably actually check my work. This is the antiderivative of 1 minus x to the negative 2. I'm going to add 1 to the power, divide by the new power, but there's also a negative coefficient there, so there's probably like another negative 1 over here. Those cancel out, and yeah, we get 1 over 1 minus x. So, right, because if you take the derivative of this, yeah, the derivative of this is definitely 1 over 1 minus x squared because the negative 1 power makes it negative, but then the chain rule makes it positive again. So check this out. We can say that the derivative of 1 over 1 minus x is equal to 1 over 1 minus x squared. Yeah, I'm going to erase some of this here. Well, I don't think you can I erase my integral here? Maybe. I can say that 1 over 1 minus x squared is the derivative of 1 over 1 minus x. But then that's equal to, well, I know the power series for 1 over 1 minus x. Right, the power series for 1 minus 1 over x is 1 plus x squared plus x cubed plus x to the 4th, and so on. I'm going to, personally, I like to differentiate the geometric series as the formula, but you can also do it piece by piece, right? You could write this as 0 plus 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the 4th, and so on, which is going to give us the power series for 1 over 1 minus x squared is going to be the sum from n equal to, let's see, I guess I want to do from 1 to infinity of n times x to the n minus 1. And if sometimes the formula is simple enough that you can just kind of see it, right? I get 1 times x to the 0, 2 times x to the 1, 3 times x to the second. That works out. Alternatively, you could take this thing here and say, okay, this is going to be, I'm going to write it down here. It's going to be the derivative of the sum from n equals 0 to infinity of x to the n. Now notice, I'm going to take the derivative of this and it's going to look a little bit different. That's okay. So if I take the derivative, I'm going to get, should look different. N equals 0, yeah, to infinity of n times x to the n minus 1. Now it looks almost the same. The only difference is this one is starting off with 0 times x to the negative 1. 0 times anything is 0, so I don't need that term. So often when we take the derivative to get the thing we want, we cut off the first term because the first term is usually 0. So this would really just be the sum from n equals 1 to infinity. Okay. So let me ask you guys, what's the radius of convergence for this? What's the interval of convergence? Well, we know that this series has an interval of convergence from -1 to 1, right? Your usual geometric series with the ratio being between -1 or the, yeah. Now this, and this is where things are very subtly different. Maybe not that subtle. This is geometric, right? Each term you multiply by x to get to the next term. This is not geometric, right? We don't, right? You multiply 1 by 2x to get this. You don't multiply 2x by 2x to get that. You multiply it by 3/2 x. You multiply this by 4/3 x. You multiply this by, right? It's not geometric. You're not multiplying by the same thing each time. So let's talk about finding the interval of convergence for this. Now, yeah. I'm going to tell you the result after we do it. So the way we would normally find the interval of convergence would just be by doing the ratio test. So ratio test. I'm going to take the limit as n goes to infinity of an plus 1 over an for my series, which is the series from n equals 1 to infinity of n times x to the n minus 1. Let's see what we get. We get the limit as n goes to infinity of n plus 1 times x to the n over n times x to the n minus 1, which ends up being, let's see, n plus 1 over n, the limit is 1, and x to the n over x to the n minus 1 is just the absolute value of x. And for the series to be convergent, the ratio test has to have a limit that's less than 1. So look, we get the same interval of convergence. Well, and I shouldn't say that actually. We get the same radius of convergence and the same center. So this series here, we know the interval of convergence is -1 to 1. Because for geometric series, we never include the endpoints. But for this series here, we get -1 to 1, but it's unclear if those are excluded or included or one of each. What I'm really trying to say with a lot of words is we have to test the endpoints. So if you ever differentiate or anti-differentiate and make your thing now not a geometric series anymore, this radius and the center of convergence are still the same, but the endpoints might not have the same behavior. So let's check real quick. If x equals 1, I've got the sum from n equals 1 to infinity of n. Well, that's clearly divergent by the nth term test, right? N goes to infinity, which is not 0. If x equals -1, you got the sum from n equals 1 to infinity of n times -1 to the n minus 1. Divergent for the same reason. Still, the limit of this is not 0. So in this case, the interval of convergence is, in fact, -1 to 1. It's the same. But what I'm trying to say in a lot of words here is that when you do a derivative or antiderivative to help you find the power series for your function, the entire interval of convergence stays the same, except for the endpoints might change behavior. So let me write that down because that's kind of a big deal. It's actually pretty cool. I mean, there's that, and it's definitely a theorem we can prove. I don't think we prove it in this class, but definitely prove it in another class. It's not hard to prove. I mean, it's a little hard to prove, but it's not like super hard to prove. So here is the gist: integration / differentiation of a power series. If we integrate or differentiate a power series that converges for x between, I like to write it, I'm gonna write it slightly differently. Not between r and negative r, but because your center might be different. So it could be converges for x between a plus r and a minus r. Then the new series also converges for x between a minus r and a plus r. And then the only thing is we have to test the endpoints. I should point out that when I say it converges for x between these things, I'm also implying that it diverges if x is outside of that. So this series is also meant to diverge if x is bigger than a plus r or less than a minus r. So that's kind of the whole gist. If you know something, if you know some series is convergent on some interval, its derivative or its antiderivative is also convergent on that interval, and then we test the endpoints. So I get some cool examples. Yeah. So we can use this idea to show some cool series converge and diverge, or to find some series, I guess. So like, for example, I could ask, what's the power series for the inverse tangent of x? Now, we can totally do this when we learn the Maclaurin and Taylor series stuff a different way, but the name of the game for a lot of this stuff is you want to try and take the easiest path to get to your answer. I don't want to do all the, like find all the derivatives and find a pattern for the derivatives, which is what the Taylor series stuff is going to have us do. Instead, what I would really like to do is say, well, I know the derivative of inverse tangent of x is 1 over 1 plus x squared, which is 1 over 1 minus negative x squared. And so then I can say that 1 over 1 minus negative x squared, I know a power series for that. It's 1 over 1 minus some stuff. That's just, sorry, first term is 1. 1 plus negative x squared plus negative x squared squared plus negative x squared cubed. That's just the sum from n equals 0 to infinity of negative x squared to the nth power. Or as I would probably prefer to write it, I'd probably prefer to write that 1 over 1 plus x squared equals the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n. Right? I'm thinking of this as negative 1 times x squared all to the nth power. And the reason you want to do that is because if you're differentiating or anti-differentiating, that -1 to the n can be kind of throwing you off. But if we pull it out in front, it just is like a constant multiple, which we don't have to worry about. Okay, so I know that the antiderivative of this is equal to the inverse tangent. So the inverse tangent of x is the antiderivative of 1 over 1 plus x squared, which is just the antiderivative of this. But if you're anti-differentiating a sum, you really only have to anti-differentiate the thing inside it. So this is going to be the sum from n equals 0 to infinity of -1 to the n times the antiderivative of x to a power is just x to the power plus 1 divided by the new power. I think this is personally a little easier. Some people would prefer to take this series, 1 minus x squared plus x to the 4th minus x to the 6th, so on and so on and so on, and actually anti-differentiate it term by term to get x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on. And then find the pattern for this, which is this, right? If you plug in n equals 0, you get -1 to the 0, which is 1, times x to the 1st over 1. And then n equals 1 gives you, sorry, that's right, n equals 1 gives you -1 times x to the 3 over 3. And then n equals 2 gives you +1 times x to the 5 over 5. I feel like there's something I'm forgetting to say here. Is there something I'm forgetting to say? Oh, I know what it is. I don't think Grant really addresses this. That's okay. Some people get caught up on the fact that when you integrate, there should be a plus c here. And then you have to check. So for this series, let's ignore this for a second. For this series, there are still a few things we need to address. First and foremost, what's the interval of convergence? Well, the interval of convergence for this is that our ratio -x squared has to be between -1 and 1. So for -x squared to be between -1 and 1, sorry, I know I'm using up like all the board space here. X has to be between -1 and 1, right? We need x cubed, if x is any bigger than 1, like 2, you're going to get -4, which is 2 negative. If x is any smaller than -1, like -2, -2 squared is going to be -4, which is still 2 negative. So we definitely need x to be between -1 and 1. So we know that the interval for this is the same, except we have to check the endpoints because maybe this wacky thing converges for one of the endpoints. And I think it doesn't, but let's check, right? I'm not sure. So I guess I'll write this on the other side so I can leave this up here because I think you guys might want to see it. Then maybe we'll try and do one where the center isn't 0. So we're looking at this, sum from n equals 0 to infinity. When you're integrating to get it, you typically keep the 0 because the first term doesn't just go away. -1 to the n, x to the 2n plus 1 over 2n plus 1. So let's check the endpoints. If x equals 1, all right, let me double check that I wrote down the thing right. That looks good. Okay. So let me ask you guys. X equals 1. Plugging in 1 is easy in that we know that 1 to any power is just 1. So plugging in 1, here's what I get. I get -1 to the n times 1 over 2n plus 1. So what do you both think? Is this going to be a series that converges or is this going to be a series that diverges? Well, it's alternating, which means it's probably going to be convergent, unless these terms don't go to 0. But these terms definitely go to 0, and they are decreasing, and it is alternating. So yeah, this definitely converges by the alternating series test. Some people are going to want you to show this. Most sane people are not. So typically when you're testing the endpoints, if you're just testing the endpoints, people are like, okay, you've done enough work. You don't also have to then do the alternating series test to show that this converges. You just be like, yeah, I can see obviously this is decreasing. Obviously its limit is 0. Obviously it's alternating. Maybe not super obvious. I hope it's relatively obvious that clearly this is decreasing, because as n gets bigger, the terms definitely get smaller. Clearly the limit of this is 0. So I think it's not unfair to say it's obvious. On the other hand, and this one's a little bit less clear, for x equals -1, you've got the sum of -1 to the n times -1 to the 2n plus 1 over 2n plus 1. So here's the question. Is this alternating? It's a good question. So probably the best way to tell if it's alternating is to combine the negative ones together. So to write this as the sum of, let's see, so -1 to the n times -1 to the 2n plus 1, I'm going to add the powers. So n plus 2n is 3n plus 1 over 2n plus 1. So the question really, if you're asking if something's alternating, you're really asking, does this power go back and forth between being odd and even? So if n equals 0, 0 plus 1 is odd. If n equals 1, 3 plus 1 is even. If n equals 2, right? So yeah, 3n is going to go back and forth between being odd and even. So 3n plus 1 is also going to go back and forth between odd and even. So yeah, this also converges by the alternating series test. Interesting. Another way you could have justified this to yourself, if you prefer, is -1 to the 2n plus 1. Since 2n plus 1 is always odd, this part here is always -1. And then this part here is always alternating, so it's alternating. So our interval of convergence here, so this converges on the interval from -1 to 1 inclusive of both endpoints. Just neat. The other thing I'll point out here, and again, I don't know if your teachers are really talking about this or not, but I said on the other side here that if you're integrating something, you have this plus constant kind of deal. So the question is, well, what is that constant? 99 times out of 100, that constant is 0. How do we check? Well, we know that a series always converges at its center. So if I look at the center, right? So if I look at the series, here's the series, which I'm going to think about that way. The center is the middle of -1 and 1, which is 0. So I can say that the inverse tangent of 0, we always check at the center, is equal to the sum from n equals 0 to infinity of -1 to the n times 0 to the 2n plus 1 over 2n plus 1 plus c. But here's the deal. Inverse tangent of 0 is 0. 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0 is 0. So 0 equals 0 plus c, so c has to be 0. And most of the time, that's what happens. You plug in your center, and you end up getting 0 on this side equals 0 plus c on that side, and the constant's just 0. If your teacher hasn't talked about this, you should just not even worry about it, because almost every time, not every time, there are some funky examples where you can actually get this constant to be non-zero, but most of the time it's going to be 0. Yeah, these are fun. So let's, yeah. Yeah. Let me see here. I feel like I want to say something else. Those are most of the derivative. So the derivative and integral examples, really, there's kind of like, we've covered the main ones. 1 over 1 minus x squared is the derivative of 1 over 1 minus x. Obviously, there's other things we can do here, right? If you had 1 over 1 minus 2x squared, you would want to somehow write that as a derivative of something. It's probably something like this. we can actually use our skills of integration to figure out what this actually, right, what the integral this actually is. But I could also just try and be lazy about it and take the derivative of this. The derivative of this is -1 times 1 minus 2x to the -2 times the derivative inside, which is -2. So this is 2 over 1 minus 2x squared. So I actually have a factor of 2 too much. So I just cheat. And I throw in a 1/2. And then those cancel out. And then I get what I actually wanted. And then you can say, all right, if I'm trying to write what this is, it's just the derivative of this. And the derivative of 1/2 times 1 over 1 minus 2x is just 1/2 times the sum from n equals 0 to infinity of 2x to the n. Sorry, I forgot the derivative. It's the derivative of this. And one more time, I'll point out, while we are certainly capable of differentiating 2x to the nth power, right, it's going to be n times 2x to the n minus 1 times the derivative of 2x to the chain rule. Make your life easier. Say, oh, I'm going to write this as the derivative of 1/2 times the sum from n equals 0 to infinity of 2 to the n times x to the n. Then you only have to differentiate this part because you're only differentiating with respect to x. So that's going to be 1/2 times the sum from n equals 0 to infinity of 2 to the n times x to the n minus 1. And then since n equals 0 makes it 0, you can say we're really starting at 1. And then you can manipulate this more, but you don't have to. So sorry, I got a little sidetracked there. So this is one of the main ones we see via differentiation. And then we also have that natural log of, the standard one is usually natural log of 1 plus x is equal to the integral of 1 over 1 plus x. And that's another standard one that we talked about last time. So we find the series for 1 over 1 plus x, and then we integrate it instead of finding the series for 1 over 1 minus x and differentiating it. And then the third one was the one we just did, which is that the derivative of inverse tangent is 1 over 1 plus x squared. So the antiderivative of 1 over 1 plus x squared is equal to inverse tangent. Those are kind of like the three standard examples of using a derivative or antiderivative along with the geometric series for 1 over 1 plus or minus x, how we kind of use those. Sorry, I know it's not quite as succinct as it could be, but that's kind of the deal. Oh, I should say though, just because I should say, right? Oh, that's all right, there we go. So, right, for this one here, I see that just to kind of sum up here, this one would have an interval of convergence where, so 2x is my ratio, so I have to have that 2x is between -1 and 1, so x is between 1/2 and -1/2. But I would have to check my endpoints here. So if I look at plugging in, right, x being 1/2, 1/2 to the n minus 1 and 2 to the n essentially cancel out, especially if you bring this 1/2 in. If you bring this 1/2 in, 1/2 times 2 to the n is just 2 to the n minus 1. So this is kind of the same as that other one where we had a derivative, right? If x is 1/2, you get 2 to the n minus 1 times 1/2 to the n minus 1. Those cancel, but the n still goes to infinity. So it diverges when x is 1/2. It also diverges when x is -1/2. So this is really actually the interval of convergence. Most of the time, if you're using a derivative of your series to get what you want, it's usually not going to converge to the endpoints. Not always, but most of the time. Whereas if you're using an integral, it's a little less words. So if you're using an integral like here, that you're integrating your thing, it's more variable. The endpoints can kind of do anything. Whereas if you're using a derivative, most of the time, the endpoints, you're going to get divergence. But not always. Okay, I think I've said enough about that. It might be time to start talking about the Taylor-Maclaurin series. I will say, I know no one from, so I have to assume both of you are in BLO's class because someone in Waldron's class was like, yeah, we're only on section like 10.4. So it seems like we're going to start having some divergence between the two classes as far as how far they are for the where you're at. So I'm going to try to kind of not jump too far ahead so that the other class doesn't feel left behind, but also I don't want to get too far behind you guys so that we can keep up. Yeah. So let's do one more integral of convergence question, and then we can, I guess I should ask both of you, do you want me to start talking about Maclaurin and Taylor series right now, or would you rather wait till next week? Now or later? We can wait. Okay. That sounds fair. So let's do a couple more integral of convergence examples that are more normal, meaning like, oh, actually, wait, there was something else that I definitely had in mind that I was looking at. Yeah, I know what it was. Sorry, I want to find it because I do think it's worthwhile. Yeah, let's look at this for 1 sec. So, because I don't think I talked too much about this, and it is something that does get talked about. How many terms? So last time we talked about how there was one problem that I think someone asked about, where we used the integral remainder, whatever, to estimate how much our error was. Well, there's kind of 3 different ways of estimating error. One of them is using the integral remainder, which is that, right? The remainder after you add up n terms is less than the integral from n to infinity of whatever your thing is. So that's one way of estimating the remainder, as long as you can integrate the series, which a lot of them are not very integrable. Another way of estimating the remainder, and this one's kind of the slickest way, is that for an alternating series. So for an alternating series, it's true that the remainder is always less than the next term in absolute value. And then the other one has to do with Taylor-Maclaurin, Taylor remainder estimation, which I won't say right now because we should talk about the Taylor series first. But specifically, I want to talk about this one. So the question that I want to ask is, how many terms of the series, the sum from n equals, what do we got here? 1 to infinity of -1 to the n over n factorial, which is clearly convergent by the alternating series test. The non-alternating series is definitely decreasing and has a limit that is 0. Sorry, how many terms are needed to estimate? Needed to estimate this sum accurately to 3 decimal places. And this is never my favorite way of phrasing a question, but it is a phrasing that comes up. So let's actually go ahead and look at that. Sorry, 1 second. Sure. So here's the nice thing. And let's write out some of the terms just so we can see this. So if I'm adding up the terms, I'm getting -1 over 1. Negative, I won't start there. I feel like no, I guess that's right. Sure. Which is going to be negative. That's okay. Plus 1/2 minus 1 over 6 plus 1 over 24. And the thing about an alternating series is that I feel like I'm obligated to explain, but basically, since you're going back and forth, right? So if we're adding up terms, right, our sum, right, we started at -1, 0, and then we're going to add 1/2, and then we're going to subtract 1/6. So whatever our next term is, we can never be off by more than that, right? If I said my sum was 1/2, well, it's either 1/2 or it's 1/6 less than that. But if I just added the first couple terms, you'd be like, okay, well, sorry, -1/2, I apologize, right? If I say S1 is -1, S2 is -1/2, I know that this estimate of my infinite sum is certainly within 1/6 of my actual estimate, because that 1/6 is the furthest away I can get from it. So that's how I'm justifying the fact that the next term, I know I erased the thing, right? If we're trying to find the remainder of the sum of the first n terms, it's always less than the absolute value of the next term. So if I want to be correct to 3 decimal places, I need whatever my next term is to be less than 0.001. So we need 1/n+1 factorial. Why n+1? Well, because I'm adding up the first n term, so I want to look at the n+1 term. I need this to be less than 1/1000. So what I really need is I need n+1 factorial to be bigger than 1,000. And this is just there's no like way of isolating n here. This is just a guess and check. So I know that, let's see, if n equals 4, I know that 4 + 1 factorial is 5 factorial, which is 120. If n equals 5, I have 5 + 1 factorial is 6 times this, which is 720. So it's going to be n equals 6. N equals 6. 6 + 1 factorial is definitely 7 times that is way bigger than 1,000. So if you add up the first 6 terms, you'll be correct to within 3 to the third decimal place, which again is always kind of being correct to a certain decimal place is always kind of iffy. But that's how you can do it. You're just trying to get it so that the next term is within the parameters we've set. Yeah. So yeah, the alternating series test one is kind of super slick. It's just like, oh, next term. The integral one is obviously a lot more work if you can even integrate it. And the Taylor one is even a lot more work. So yeah. So if you got an alternating series, you're like, we're in luck if we want to estimate the remainder. If it's not alternating, estimating the remainder is more of a process. Okay. Let me throw one more problem at you guys. Just good to practice. So the last one I wanted to do here, where'd you go? That's not you. Sorry, it's easy to lose your spot. There we are. So let's find the integral of convergence for the sum from n equals 1 to infinity of x minus 3 to the 2n over n to the 4th times 2 to the n plus 1. And again, right, if you're talking integral of convergence, you're talking ratio test. And I'm always going to ask you, oh, go ahead and go. Yeah, sorry, if you have to go, we can stop here. We can do this problem next week. Mindy, if you have to go, you're also welcome. Or we can do this problem if you want. Your call, Mindy. What do you want to do? Okay, let's do it. So I'm going to do the ratio test. It's going to be x minus 3 to the 2 times n plus 1 over n plus 1 to the 4th times 2 to the n plus 1 plus 1, which is n plus 2. Oh, what I was saying earlier was that I'm always going to ask for the integral of convergence because that's going to require us to check the endpoints. Your teacher might be nicer and just ask for the radius of convergence, which we can always find just by taking the length of the interval divided by 2. So it's the n plus 1 term divided by the nth term multiplied by the reciprocal, which is n to the 4th over x to the minus 3 to the 2n times Oh, sorry, I forgot the 2 to the n plus 1 up here. Absolute value. We only really need the absolute values around the x's. So I'm going to simplify this. Limit as n goes to infinity. X minus 3 to the 2n plus 2 divided by x minus 3 to the 2n is going to give me x minus 3 squared. Just slightly different than we've seen before. Now, I hope this might turn out to be a little bit ugly. Okay, that happens sometimes. And then we've got 2 to the n plus 1 over 2 to the n plus 2, which is 1/2. Should have made it 1/4. It would have been nicer. Oh, well. And then we've got words. Sorry. We've got n to the 4th over n plus 1 to the 4th. And things like this, the limit is always just going to be 1. So the limit of that is 1 as n goes to infinity. And we're left with x minus 3 squared. You can put the square on the outside of the absolute value. Divided by 2 is less than 1 for convergence. So here's what we've got. We need that x minus 3 squared is less than 2. So that x minus 3 is between root 2 and negative root 2. It's kind of a funky interval of convergence, which I haven't actually stated yet. So the interval of convergence, not addressing the endpoints quite yet. If I add 3 to everything, it's going to be x is between 3 plus root 2 and 3 minus root 2. Maybe with the endpoints, right? We don't know. I could say at this point that the radius of convergence is the square root of 2, because the difference between this and this, right? 3 plus root 2 minus 3 minus root 2 is 2 root 2, and half of 2 root 2 is root 2. Or basically how far we are from the center. The center is clearly 3. 3 plus root 2, 3 minus root 2. The radius is clearly root 2. To check the endpoints, we plug them in. So I'm going to erase. I know we're out of time, but I want to finish the problem. So if I plug in 3 plus root 2, let's just do it real quick. So 3 plus root 2 minus 3 is going to be root 2. So I'm going to get root 2 to the 2n over n to the 4th times 2 to the n plus 1. Root 2 squared is 2, which gives me 2 to the n. So this is the sum of 2 to the n over n to the 4th times 2 to the n plus 1. You can cancel a 2 to the n here and a 2 to the n there. You're left with 1 over 2 times n to the 4th, which is definitely convergent because it's a convergent p-series. So this one definitely converges here. It's also going to converge if we plug in 3 minus root 2, because 3 minus root 2 is going to give us essentially the same thing. It's actually going to give us exactly the same thing. Because although 3 minus root 2 would give us a negative root 2 inside here, it's going to be a negative number to an even power. So this is actually literally exactly the same. But even if it was alternating, it would still converge because it's still going to be divided by an n to the 4th, which is going to be convergent. So we do, in fact, get the endpoints here. So our interval of convergence would be bracket 3 minus root 2 to 3 plus root 2 bracket. All right, it's a cool problem. Kind of gross numbers, but it's okay. All right, that's all I've got.